So in this section, we're going to be working on the second order partial derivatives. So remember in the first section when we talked about partial derivatives, that is signified by f sub x and a partial derivative of f of x and y. So now in the second derivative, we're going to take that partial derivative that we just had and we're going to conduct another partial derivation of it to get the second order. And that's the second here with the 2 of f of xy. And that is denoted by f of xx. Same thing with the y's. And then we also have the partial derivative with respect to y of the first order partial derivative of x. So we have the second order and this dx dy down here at the bottom. Notice that this is partial. So we have f of xy right here. Now, let's take it. Remember from our first order that whenever we are taking with respect to x, everything else is a constant. So if we wanted to find the partial derivative of, say, x cosine of y plus y e to the x, we're going to take the partial derivative with respect to x first. That means this goes away because it becomes 1, and cosine of y is the constant, and the derivative of e to the x is itself, so the y is a constant, so we get y e to the x. If we take the second derivative, we're going to do it again with this. So cosine of y is a constant, so that becomes 0, and again, e to the x gives us y e to the x. Now, let's do the same thing for the y's. X is a constant now because we're taking the derivative with respect to y. So cosine of y, the derivative is negative sine, so we get negative x sine of y plus y, the derivative of y is 1, e to the x is a constant, so that stays. Let's do it a second time. Well, again, x is our constant, sine of y, we're taking the derivative of that, so we get negative x cosine of y, and here, e of x is a constant, so that becomes 0, and that's all we have left. So that's how we get our second derivatives. Now, let's take a look at the partial derivative with respect to y of our partial derivative, our first order, with respect to x. And so that's going to give us, if we take this, we're going to get negative sine of y plus e to the x. So it raises a good question. If we were to swap the order and take the derivative of with respect to x from this right here, our first order with y, does that yield the same answer that we got over here? Well, let's take a look. So if I want to take the second derivative, this time dy dx, I'm going to get, taking the derivative, remember sine of y is now the constant, we're taking the derivative with respect to x, makes it negative sine of y, derivative of sine of e to the x is itself, so that's e to the x. And so yes, it is. So let's look at another example and see if this is still true. So again, we're going to take our first derivative. And so the derivative of x to the fourth is 4x cubed, y cubed, and that actually becomes 0 because we're taking with respect to x, y is a constant. Let's do our second derivative. Well, derivative, remember y to the y cubed is still constant, so we're going to take derivative of 4x cubed. Well, 4x cubed becomes 12x squared. And then we have the y cubed there on the end. So let's do dy. We have the derivative of y cubed is 3y squared. So we're going to get 3x to the fourth y squared. Derivative of y to the fourth is 4y cubed. All right. So we can just complete it by doing this. Not that this helps us, but let's do it anyway. Second order with respect to y, we're going to get y cubed with a 3 in front there. That gives us 6x to the fourth y minus 12y squared. Now, let's do the derivative with respect to y of this, our original first order with respect to x. So we're going to remember now we're taking the derivative with respect to y, so 4x cubed is the same. You get 3y squared from here, so 4x cubed times 3y squared, that's going to give you 12x cubed y squared. So let's flip the order around, and now we're going to start with this one and take it with respect to x. And if we do that, we're going to get x to the fourth becomes 3x cubed. So that becomes 12x cubed y squared. This is a constant. So, of course, those two things are equal. Well, that brings us to this theorem, Clairaut's theorem. And it says if f of xy and its partial derivatives are defined and continuous, then f of xy is equal to f of yx. And we've seen that in both of these examples here, this one and this one. So let's talk about a few uses for this. We have quadratic approximation, which is approximating the function at a certain point using a quadratic equation. Now, taking the time, I've taken the liberty of just going through this problem and doing it myself instead of turning this into a 35-minute video. But the point, the exercise requires us to go through each of our derivatives, f of x, f of y, f of xx, f of yy, and x of xy. And we have to evaluate those at each of these at this particular point. A couple words of caution here. Don't forget to do this. Don't forget that this term, especially if it's being evaluated at 0, then we're going to end up with x minus 0 here, and that can easily be forgotten. Same with the y's. Remember, we have x minus a squared here, the 1/2 on each of these, but there is no 1/2 here with the cross derivative. So x minus a, y minus b, that's another thing to miss. So when we put all this together, all these evaluated partial derivatives, we work this out, we get a quadratic. So notice negative 2x squared minus 12y squared and so on. So we get a quadratic approximation at that point. Now, very common, like I mentioned, is to do the 0, 0. That eliminates the a, the b from these terms, but that makes this also very easy to forget. So don't forget to do those. These are actually very interesting exercises. So let's look at a couple of other fun uses for this. So this is Laplace's equation. It says that there are certain functions out there that we take the second derivative with respect to x and the second derivative with respect to y, and it equals 0. So let's see if this function satisfies Laplace's equation. We're going to start with the first order partial derivatives. We do this. This is our constant. This becomes cosine, so we get 1/2 e to the y minus e to the negative y cosine of x. And if we do it again, remember that this is our f of xx. we're going to get, this time now taking the derivative of cosine as negative sine, e to the y minus e to the negative y sine of x. All right, let's take the second derivative, or the derivative. We're going to start with our first order derivative of y. Now, the 1/2 and the sine of x are, of course, constants. And so now we have the derivative of e to the y, which is itself, plus, remember, we're going to take this derivative of e to the negative y. That gives us a negative e to the negative y. You have a negative sign already, so that's a plus. Let's take the second order derivative. Once again, 1/2 sine of x, e to the y. Again, another negative comes out of here, e to the negative y. And if you notice, if I were to add these up, I would get negative 1/2 sine of x, e to the y, e to the negative y, plus 1/2 sine of x, e to the y minus e to the negative y. And that, of course, cancels each other out, and so you get a 0. And so this is how we know it's a Laplace function that satisfies Laplace's equation. The other application that we find, and this comes up in partial derivatives, partial differential equations, is the wave and heat equation. So it says that the second order with respect to t is equal to c squared, second order with respect to x. So we need to find both of these first, and then multiply the 1 with the x by c squared and see what we get. So let's do that. First, we find our first derivative with respect to t. Well, cosine 4x plus 4ct. So we're going to take, remember the chain rule, we're going to take negative sine 4x plus 4ct, and we're going to multiply it by the derivative of this with respect to t, which is, this is 0, this becomes 4c. So we'll just rewrite that real quick. Now, let's take the second order with respect to t. So again, 4c is a constant, sine, it becomes cosine, so negative 4c cosine of 4x plus 4ct times the derivative of the inside, which we found out before was 4c. That gives us negative 16c squared cosine of 4x plus 4ct. All right, so now let's work on the x part. So we're going to take the derivative with respect to x. Again, we get negative sine 4x plus 4ct. But this time with respect to x, not this. This becomes a 0. And we get a 4. So let's put that 4 out in front. Now, the second order with respect to x, we're going to get, again, another 4. This becomes cosine again, 4x plus 4ct, and again, it spits out another 4. And that gives us negative 16 4x plus 4ct. And this is starting to look pretty suspicious, so let's take a look at, we're going to find out negative 16c squared cosine 4x plus 4ct is, of course, c squared times negative 16 cosine 4x plus 4ct. And there you do have, that satisfies the wave and heat equation. And that's it for second order partial derivatives.